Hi there, welcome to Xamarin University. My name is Mark Smith, and I'm going to walk you through using async and await in your mobile applications to keep them responsive. Our goal today is to work with the new C# async and await keywords. We're going to take a look at why they were created, how to apply them in your code, and finally, how they work under the covers. Let's start by defining the problem and what Microsoft has done to solve it. First, let's define what we mean by asynchronous programming. Keep in mind that we're going to focus on mobile development here in this class, and so all of our examples are going to use that as our paradigm. But also keep in mind that all of the things that we talk about apply to other application styles as well, particularly applications which provide some sort of user interface component that a live human interacts with. So what do we mean? Well, synchronous means to perform something here and now, and I'll regain control to execute something else when it's finished. Asynchronous, on the other hand, means to initiate something here and now, and I'll regain control to execute something else immediately. The primary goal for asynchronous programming in mobile apps is to ensure that our applications continue to be responsive to the user, while still allowing the application to do other activities behind the scenes. These other activities might be I/O related, such as reading or writing to a file or to a database, or perhaps using a network service to retrieve information. Or these activities might be background operations, which require the use of a background thread to perform some data processing. And all of these asynchronous operations, file I/O, web services, or even long-running data processing all take time to finish. And the question we have to ask ourselves is, what do we do while we're waiting for these operations to complete? In the real world, we have similar situations. For example, when you go to the doctor, you often have to wait until the doctor is available, and while you're waiting, you could take a nap, or you could do some other activity which may or may not be related to the doctor visit, such as fill out paperwork or catch up on your Hollywood gossip. If we apply the same reality to our programming, we have the exact same choices. While our operation is running, we could sleep, in other words, block, waiting for the results to return, or we could continue doing other things which again may or may not be related to the I/O or the CPU operation that we're working on. It turns out that waiting for our operation is the default approach, and it's one that many programmers take because it's easier. Your code is simpler, easier to read, and easier to write. However, just like our doctor visit, it's not an efficient use of our resources. And so this is what we're going to focus on today, showing progress or continuing to do other operations while our asynchronous activity is actually running. If we want to be able to do other things while blocking operations are occurring, then we need to make them asynchronous. This just simply means we need to run them in parallel to our main thread that the operation is actually invoked on. And .NET has several built-in APIs to allow for this. The first is the async programming model. This was introduced with .NET 1.0, and it involves a pair of methods, a begin and an end. The begin method kicks off the operation on some other thread, typically a thread pool thread, and then returns an iasync result to track that operation. We pass this iasync result into the end method to actually retrieve the final value or the result. In .NET 2.0, Microsoft added a new pattern that we could use called the event-based asynchronous pattern. This was particularly popular in Silverlight, which moved almost all of the async APIs to this approach. This uses a single method to start the operation. The method is suffixed with async to make it obvious that it's async, and it has an event which is called when the operation is completed that actually is past the results. This approach is simpler because it manages the async operation using a delegate, which was familiar and easy to work with. But it doesn't support polling or any sort of progress reporting, and the lack of the iasync result meant you couldn't easily combine the results with other pending operations. So developers were often confused about the lifetime of the event async pattern because they weren't sure if they needed to get rid of the object after they were finished and create a new one, or if they could reuse it. In .NET 4.0, Microsoft took a hard look at how async operations were done and combined these two approaches into what we have today, the task-based asynchronous pattern. Methods are suffixed with async, just like the event async pattern. And this pattern returns a task which allows you to wait, to poll, or to get a callback when the operation is finished, similar to our original async programming model. The task also provides the ability to retrieve the result directly, so there's no need for an end method with this approach. This is the preferred approach going forward, and this is what we're going to be using for most of this class. So as you saw in the lab exercise that we just did, doing asynchronous programming requires us to write our code in an inside-out fashion, where the processing of the results is often separated from the invocation of the operation itself. Here's our basic example. we're going to use a web client here to retrieve some data from a web service. Now, the problem with this code is it's not very readable. Our brain can't very easily parse out what's really happening in this code because it's written in a non-linear fashion. The processing logic is defined separately and it's out of scope from the initiating function. And the ordering is important here. We have to wire up the completed function first, otherwise we introduce a potential race condition. Lambdas and anonymous methods make this a little easier to work with, but it's still hard to actually parse in our brain because the processing code is not executed until the async operation is complete. And so it's out of order in terms of the order that we actually have to write it in. So notice as well that exceptions and errors are reported through a property. We can't just use try-catch in the normal way to process our errors. And then finally, the method that actually starts everything off is actually the last thing that we do. This begins downloading the data, and then some point later in time, we'll execute the code associated with the event to process the results. Ultimately, we're breaking the code defined in this method into two chunks, and each is going to be executed separately as a result. It becomes more complicated, and it's harder to read, and it's certainly harder to write. So let's stop for a second. Let's think about how we'd really like to write this code. What we really want to do here is we'd like to write this code in a linear fashion because it's easier for our brains to work with. That's the natural sort of way that we parse things out, and this is exactly why most developers prefer the synchronous approach. We're going to call a method to actually retrieve the data, we then process the results, and we use try and catch to actually parse out our errors. The problem here is that download data, as you can see here in the slide, is actually a blocking call. And so we'd like to write our code this way, but we want to make it asynchronous so that we can more efficiently manage our resources. Microsoft wants this as well, and they realize that most applications will benefit from asynchronous code. We often get better performance and certainly better utilization of the hardware that we have available to us. The problem is that async code is hard to write and understand, and so many developers just don't bother. Microsoft wants to change this, and so in C#5 they introduced two new keywords into the language which dramatically simplify writing asynchronous code using the task-based asynchronous pattern. Most of you have probably used them, or at least seen them in some code already. They are async and await. And so let's look at how they actually get applied. With these new keywords, we can write our code pretty much how we want it to be. We place the await keyword in front of the asynchronous operation itself. There are rules we'll get into on this, but for now notice that it's decorating the download data method. We then decorate the method itself with the async keyword to tell the compiler that this is going to be an asynchronous method and that it's going to be treated a bit differently. We'll again see how differently in just a moment. The cool thing about this is now all of our processing code is exactly where we want it to be after the asynchronous operation. There's no events to be wired up, and the code is defined inline just like the synchronous model. In addition, notice that our errors are being reported as traditional exceptions, and so we just use try and catch just like we normally would in synchronous code to process them. So now that we've defined the keywords, let's talk a little bit about the rules for how we use them. Let's start with the async keyword. The async keyword is always applied to the method implementation. So we don't apply it to interfaces or abstract methods. It's only on the implementation itself, and it has to be added before the return type, but it can be mixed with other modifiers such as the visibility modifier or the static modifier. It's not considered part of the method signature itself, so overrides or virtual methods that use async do not also need to be declared async. The presence of the keyword on the method allows you to use the await keyword inside the method body. It essentially turns await into a keyword for the method. By taking this approach, Microsoft ensured backward compatibility for the compiler so that the use of the value await in other contexts would continue to compile properly for existing code, because async was not applied on the method. Then we have the await keyword. Await can only be applied to awaitable expressions. These are operations that complete or return a value at some point in the future, but not immediately. Most often, these are asynchronous operations such as I/O or some sort of CPU calculation, but they could also be UI operations, for example, dismissing a message box on the screen. We don't know the result until the user clicks a button. It requires user interaction, and the period between the time that we show the message box and the time that the user actually clicks a button to select a choice is indeterminate. We don't know. It's asynchronous because there's some other intervention that has to occur. The application of this keyword has a dramatic effect on the final code that the compiler is going to generate. Remember our asynchronous example in the beginning. The processing function cannot run until we have data to process. That was the reason for the event callback, to let us know that the operation is completed and that we have data to work with. Now, we're going to write the code in a linear fashion, but it's going to execute just like the asynchronous code that we started with. That means that this processing code cannot be executed until the data has been downloaded from the server. So the compiler is going to rewrite the code for us to take all of our processing code that we have highlighted here and ensure that it's run after our asynchronous operation completes, allowing the CPU to work on other things until that happens. It will effectively pause the method itself, returning back to the caller, and then at a later point in time when the operation is finished, come back and finish the execution of the method, just like our event-based example did. The big difference here is that it's going to let us write the code as if we were actually running this code synchronously. But under the covers, the compiler is going to break this method up into two chunks and execute them separately, just like our original event example. We're going to dive deeper into the magic of what's really happening here, but keep that concept in your head that the compiler is going to restructure this code and create two different things that are going to execute independently. So we can use async and await on regular methods. What about delegate methods or lambdas or anonymous delegates? Because lambdas and anonymous methods are really rewritten as regular C# methods by the compiler, the keywords are totally usable here as well. You add the async keyword onto the expression definition before the parameter list or before your empty parenthesis. Await can then be used in the body of the lambda, just as you can see here. Again, just like before, you can only apply await on something that is awaitable, what we call awaitable expressions earlier. So let's talk about what that really is. There are actually several forms of awaitable expressions that the await keyword supports, but in .NET, the most common is a method that returns a task. Returning a task from a method generally indicates that some portion of the method is going to complete asynchronously. We talk a lot more about tasks in the next class that follows this series. And so if you're not very familiar with tasks themselves, make sure to take that next class. Here we're going to use a task that eventually returns a byte array. We call this a future, or in some languages, a promise, because we're promising to return a byte array in the future. By convention, the methods are named with an async suffix to indicate that they're asynchronous. This isn't actually enforced by the compiler, but it's a good practice that's followed by the .NET framework types, and you should follow this practice in your method definitions as well. Now, one quick thing I want to point out here is that await does not know anything about how the operation will be completed. It doesn't create a thread or even require that a thread is used. The awaitable operation might use a thread, or it might use some other technique. For example, here we're wanting to output some values, pause for 1 second, and then output another line. We're using a timer delay method, which is our own custom method that happens to return a task that waits for a specified amount of time before being completed. In this case, it's possible that the implementation of our delay method uses some kind of timer callback notification. Maybe this is Xamarin Forms, for example, and we use device start timer. Await doesn't really care about the details. It's really only interested in coordinating the work, ensuring that the statements which follow the await are not executed until the awaitable expression is completed. How the awaitable expression performs the asynchronous operation does not matter. It's irrelevant as far as the keyword is concerned. It's completely an implementation detail. So here's a quick example. This code will compile perfectly and it applies async and await properly to the methods. The schedule work method returns a task, which is awaitable. However, it's going to execute the work synchronously and it will lock up our UI while it runs. And so even though we use this async keyword, our code is not asynchronous in this case because the task being returned is not something that's going to run asynchronous to our existing code. The way that we fix this is that we have to get our schedule work method to run the code on another thread in this case, and so we need to create a task. Again, if you're not familiar with tasks, that's okay. The next class in the series goes through all the details, but in short, task.run, as you can see here, will take the past delegate and it will execute it on a worker thread, and it will return you an awaitable operation in the form of a new task. The key takeaway here is that await is all about composing and managing the asynchronous operations so that you can write more understandable code. It does not actually cause your code to be asynchronous. That's up to the awaitable expression that you're going to apply the await keyword to. Remember from our earlier example that await causes our method to pause forward execution until the asynchronous operation is completed. Since we don't want to block the thread and wait on those results, we need the thread to be doing something. That something is to return back to the caller of the method using async and await and to continue executing code from there. This can be a little hard to visualize, so let's walk through an example. Let's start in a button click method. This is called on the UI or the main thread of our app, and it's going to begin executing statements to adjust the UI. It first calls a method read from URL async. That method will then create a new web client object. Then it calls a method to download some data asynchronously, and this method returns a task, which we then use the await keyword on. We cannot continue forward execution in this method, so it returns a task back to the caller method, on click in this case. Once we return, notice we've got an await on this call as well. That again means we cannot continue forward execution on this method, so the UI thread then returns back to the operating system that reported the click. At this point, we're doing some I/O operation, and neither method actually has finished all of their code. The I/O is being done asynchronously, and our main UI thread is doing more UI things, keeping our UI alive and responding to additional user activity. At some point, the I/O will complete, and when it does, the UI, or the main thread, will return back to our read from URL async method to finish the method. It will take the data result, and it will get a string from it, load that data into the UI or process it in some fashion, and that finishes the execution of the method, and so the thread returns back to the operating system. However, this also completed the task that we returned back to onClick to represent this method finishing, and because we use the await keyword on that task, that causes the main thread to return back to our onClick method and pick up where it left off. This will then reset the indicator and then finally return back to the operating system. So here's the timeline approach to our method calls. Notice again, we've got our UI thread. We call read from URL async. That then invokes the download data task async. Notice the async suffix. That hands us back a task. We do an await on it, and then we begin reading from that URL. We're doing some sort of I/O. The blue line represents some other thread or some I/O operation that's occurring that's asynchronous to our main thread. Then we begin doing regular UI activity. So our application code itself is simply responding to the UI and doing UI things. At some point, the I/O operation completes. We come back, we call getString to be able to retrieve our data. We then load that data, and then we continue on. And so you can see what await does is it coordinates these activities together. This jumping around in our code might look a little bit like magic, and it may be a little confusing. So let's go a little bit deeper to see how it's implemented. All of this work is actually done by the compiler. The CLR was not modified to implement this feature, and other non-Microsoft languages in .NET don't necessarily have this support. We mentioned earlier that adding the async keyword allows you to then use the await keyword, and that's the primary reason for this async keyword itself. But today it actually does one other thing to your method. It causes the compiler to change how it actually compiles your code. So let's look at an example. Here we've got a very simple say hello method which outputs a string to the console. When you compile this with the C# compiler, it will actually turn this code into MSIL, or intermediate language, which is a simple CPU-independent set of bytecode instructions that can be efficiently converted to native code. It either does this at compile time for iOS or at runtime for Android and Windows Phone. The IL code is very similar to the original C# code, and it's not terribly hard to understand. Here you can see that we're loading a string called hello world. We're then calling a method called console_writeLine that sits in the system namespace in the MS Core live assembly. Now, let's do this again, but this time, let's add the async keyword onto the method. No other change to the method, just simply adding async, and let's look at what happens to the IL. So notice first that the method signature has not changed. It's still just say hello, it's managed, and it returns a void return type. There are no additional keywords added to denote the presence of the async keyword in terms of the method definition of the IL. This is why it doesn't impact virtual methods or overrides, and also why it's not added to interfaces or abstract methods which have no implementation, because the async keyword only affects the implementation of the method. However, the generated code is quite different. First, notice that we're now creating a local variable in the method. The type of this value is bracket say hello bracket d__1, which is certainly not something that we wrote. Instead, it's a compiler-generated class which was created on our behalf to manage the asynchronous nature of this code. And as you're going to see, it will hold the state of our asynchronous method. Second, notice that we no longer have a call to console_writeLine. Instead, we're calling a MoveNext method on the compiler-generated class. This is actually the secret to how async and await chunk up your code. They rewrite it as a set of steps that need to be executed in order to complete the method, and they use this MoveNext to actually drive them between the steps. Now, if you've done anything with iterator methods in C#, this code probably looks very familiar because this is very similar to how C# implements iterator methods. In fact, the code generation engine appears to be shared between those two features today. Finally, notice after MoveNext is finished, our sayHello method returns back to the caller, except we never called console writeLine. That code was moved into our compiler-generated class, and more specifically, into the MoveNext method itself. For this simple method, MoveNext has a very simple implementation. So here's where we find that call to console writeLine. In more complicated async methods, you're going to find that this MoveNext method will switch on a state parameter and execute different code based upon the current step. In addition, notice that our method got a little more complex in that we're now capturing exceptions that might happen. This is how we can handle exceptions that occur from our asynchronous operation and report them back properly to the processing loop. Recall that in our event async pattern implementation, that was actually reported as a property. Switching back to our read data from URL method, it's going to have the same sort of complex compilation. Ultimately, what we're really doing is turning our method into a state machine. The presence of the async keyword will cause the compiler to generate a state class to manage the state of the operation. In this case, it will be read data from URL d__1 instead of sayHello, but the purpose is identical. It has a MoveNext method to transition and execute chunks of our code. It captures all of the local variables needed for our code chunks into this heap-based instance, such as the byte array, the web client, and the converted string. This is important because all of these values need to exist longer than the call to the read data from URL method. Remember, we're going to return back to the caller when we hit the await method. Normally that would clean up the stack for the method, which would get rid of all those objects. So to keep them around, the compiler actually moves them into this instance class that it creates. The MoveNext implementation then runs the state machine for us. It starts by creating a web client and issuing a call to download data task async. In the state machine, it then calls a method on the return task for the download data task async called getAwaiter. This is a convention that's required by the await keyword, and all awaitable expressions expose that method. The getAwaiter method is required to return a type that provides three members on it: isCompleted, onCompleted, and getResult. There's no interface or base class. The compiler just looks for that type information and binds to those members directly. In fact, the type is actually often a structure instead of a class for performance reasons. The compiler then generates code that uses these members on the returned instance to check whether the object's already been completed, uses the isCompleted for that. If it's not, to hook up to a callback using the onCompleted member that then calls back into MoveNext when the operation finally does complete. Assuming the operation wasn't already completed, MoveNext changes the current state of the machine so that when onCompleted callback is invoked, we actually execute the next chunk in our process. Then it returns from the MoveNext method back to the original read data from URL caller, which will then return as we saw in the sayHello IL code. At this point, our operation is running and our UI thread is off doing UI things. Then at some point, our async operation will complete and the completion handler will call back into MoveNext. Since our state is now 1, because we changed it earlier, we will then execute the next chunk to process the result from our operation using the getResult method on the awaiter to get the final value from the async operation. Exceptions are caught and captured as part of the results. This then allows the compiler to rethrow the exception later when the client awaits the return task. Finally, notice that the state machine is set back to a -1 state to indicate that it's not running and that the state machine itself is marked as having a result, which can either be a return value or an exception. Async await are pretty awesome, and the compiler is taking some pretty severe liberties with your code when you apply them. However, there's one area where the implementation of all of this leaks into your code, and that's the return type of the methods that have await applied to them. Recall that in order for something to have await applied to it, the method must return an awaitable expression. That means a task or a task of T in .NET. However, notice that the variable that you assign from that call doesn't actually reference the task. In this case, it's just a byte array. It turns out that the await keyword is managing this on your behalf. It ensures that the calling method does not continue until the task being awaited is completed. And at that point, the return value is pulled out of the task and assigned to your value, and your logic continues, or an exception is thrown to indicate some sort of failure occurred in the asynchronous method. This is all done by the compiler using the information that it collected in that MoveNext implementation. This implementation detail leaks into your code as well. Up to this point, we've been returning void from the read data from URL method. But what if we actually wanted to do processing on the data in some other method and just have this method return the data itself? So we change the return type to a string and we try to compile it and immediately run into a compiler error that says we have to return void, task, or task of t. To understand what's happening, let's ask ourselves a question. Where does this method actually return to the caller? Remember that the usage of the await keyword causes the code to actually return back to the caller after starting the asynchronous operation. So we can't really return a string at that point because we don't have the data to create it yet. Instead, we have to return something that will let the caller eventually get a string at a future point in time. So that something is, of course, a task of t, a promise of a future value. In this case, the string we will eventually produce once the asynchronous operation is finished is what we're going to return. The compiler takes care of creating the task of string for you. It's actually part of the state machine itself, and the MoveNext method that we saw earlier will then complete that task when the state machine itself is finished. So we can't just return anything from a method marked as async. The compiler requires that we return one of three types. First, as you just saw, we can return a task of t. This is what you should almost always return if you have a result coming back from the method. The t represents the result itself that you want to process. Next, you can return a simple task. This is a non-generic version. This is if you have no result. In other words, if the method would have been a void return type if it were synchronous, then you should use a task as the return type for the asynchronous method. Because it's a task, that allows the caller to then apply the await keyword to your method. Finally, it's also possible to use the void return type. However, this is reserved predominantly for event handlers. In other words, where you're implementing a delegate signature that requires void or a virtual method that returns void and you can't control the return value. Now, this is actually quite important. Be very, very careful with async void. It is allowed because we need to be able to perform async operations inside of delegate or virtual method signatures, but it's very, very dangerous. First, the caller cannot await your method. That means that your method is always a fire and forget method with no ability to get any sort of result or even know when it's finished. More importantly, because you cannot await the method, you also cannot catch exceptions that occur in that asynchronous code. That means you don't even know if the method finished successfully. The bottom line is you should never use void return types with async and always return task unless you happen to be implementing a virtual method or a delegate signature where you have no choice. As we close out this topic, there are a couple of limitations that you should be aware of when you're using async and await. First, you cannot have out or ref parameters on your async methods. This makes sense if you think about it. All of your parameters have to be captured and put into the state machine object. There's no way to do this for reference-based parameters in C#, so this is simply a restriction of the platform that the compiler is going to enforce. Next, you can't use await inside constructors or property getters. This also makes perfect sense. Constructors and properties have to return immediate values. Since async methods always return tasks, you can't apply them here. You also cannot await methods inside of a lock statement. This is less of a technical restriction and more of a design restriction. Awaited methods complete asynchronously, and generally holding a lock for long periods of time is a fairly bad idea. So C# simply disallows this. If you need to do locking of some sort, you can use monitor enter yourself or use a different synchronization mechanism. In fact, many of the newer synchronization mechanisms actually allow you to use the await keyword with them, so they'll do the synchronization with this sort of parallelism idea in place. Be aware that await used to be disallowed in catch finally blocks, but that was changed in C#6. You can now actually use await inside of a finally or inside of a catch block. Finally, await is only allowed in certain places in LINQ queries, specifically only in the first select or the first group statement. Again, you can restructure your code to resolve this if you happen to run into it. So hopefully now you have a good understanding of how async and await get applied to your code. This is just the tip of the iceberg, and we decided to start here with the async and await keywords because this is more of an application of using them, and there are so many methods in .NET that return tasks that we thought that this was a good place to start. How do we actually use these keywords to better structure our code so that we can use these nice async methods in the framework and make our code more readable? But what you're eventually going to run into is wanting to create your own asynchronous code. In other words, where you would like to execute something in the background and then be able to apply these keywords to that something. That's what our CSC351 class is all about. It's going to go much deeper into the task parallel framework where we get that task class, show you how to use the task class, and actually what happens under the covers.